We were looking at integration as something that we might need to do in some problems, and the application that I was trying to motivate here was how much heat can you predict is going to be radiated off, or how quickly is energy dissipated by a cooling fin like this. And the challenge with that is that the temperature that or the energy you lose is driven by temperature differences, and that is not the same as you look at a fin like this. You have cooler bits at the tip and hotter bits at the very base where the heat's coming from, and so it becomes actually a fairly complicated thing to decide how much heat is going to be radiated, because the temperature difference is not constant as you move down the fin. We also found out that the temperature itself was a not so simple function with a bunch of hyperbolic cosines and hyperbolic sines, which are really exponentials in disguise, but it looks stunning and impressive. And it's especially impressive when we think the next step dealing with that temperature would be to slap an integral sign in front of it and then find an antiderivative of that complicated menagerie of constants. We might not want to integrate this by hand. We might want to take advantage of some other tool to get an integral value. That was our goal last class, and we found one pretty straightforward way to do that. We said, well, basically we have a curve like this. We have some function, f of x, that's the blue line, and the integral has that area interpretation. So if we want to find this area, we can find the integral of that, and that'll give us the same thing. The area and the integral will be the same value, same amount. And then we said, well, wait a minute. Areas, we know about areas of very simple shapes like rectangles. And if we go back to the roots of integration, hey, function times delta x, function times delta x. There was a sum that this came from called the Riemann sum that actually inspired the integral notation. So if we could add up f of x's times delta x's, then we could get roughly the right area. It'll be an approximation, but at least it'll get us somewhere. And we're going to adopt a consistent notation here, where we're going to integrate over some interval from a to b. Our function's going to do what it does. And we're going to break that into subintervals. And we're going to divide it into n subintervals. I'll just call them n intervals, which is n plus 1 boundary points. There we go. And when we do that, that integral that we saw before turns very nicely into a sum that can be expressed in MATLAB. Hey, I'm going to take the function value, so I'm going to go up to my function here. This would be f of x1. And I'm going to build a rectangle out of that. That's going to be delta x wide. Well, I'm going to take f of x1 times delta x. And then I'm going to go to the next interval. And I'm going to do the same thing with a rectangle of height f of x2 and draw a rectangle and so on. And we saw that last class that actually did a pretty decent job so long as we had a lot of intervals, right? So the idea is basic. I've got a function. I want to find the area underneath. I can approximate the area by taking heights times widths and just doing that a whole bunch of times until I get to the end of my interval. The thing we found, of course, was that, as I just mentioned, the more rectangles you use, the more accurate it becomes. So that's fantastic. As we increase the number of intervals, we get more accurate. But there is a trade-off. It's also more computational work. I have to do 500 iterations through a loop or 500 sums to do this. I only have to do 5 iterations through a loop or 5 sums to do that. And there's a natural trade-off, how much work for how much accuracy. But even more than that, we're going to find out that there's absolutely better ways to go, because we can't just say that one method's going to be more accurate than another. But what we could say is, if I'm willing to do this extra work, how much more accuracy or how much less error can I get if I'm a little just this much smarter about how we build our areas as we go along for each panel. Left-hand rule and right-hand rule are crude. We can do way better just by drawing pictures and saying, hey, there's a better way. If you think of what we had to do to get the left-hand rule, well, we had to evaluate the function at the first point. And then for the next interval, we had to evaluate the function again to get the height of the second rectangle? Well, if we have those two heights already, this height and this height, well, why don't we not make rectangles? Why don't we connect them with a straight line? And already we can see that the error, which is the difference between the real curve, or the area under the real curve, and the error in the straight line or box, it's way better if we do the trapezoidal rule. And that's going to be true in general because the straight lines are more flexible. They're going to capture the shape of the curve better than a horizontal line will. So it's a good place to start. We expect this approach, which involves the same idea, finding heights, building an area that we can calculate, and seeing what area we get in total, is going to be pretty effective. We should get a formula for that, though, so it's not too bad to do this. What we've got here is, we'll do it on a general interval. So instead of x1 and x2, or x10 and x11, it's xi and the next x, xi plus 1. And these function values here are going to be f at that value and f at the next x value. And there's a couple of ways you can slice this, but the way I like doing it most is if we cut it and we take this triangle here and flip it over, where do you think we would cut to get that perfect flipping over and replacing the left-hand triangle and slotting it in on the right-hand side? How far between the 2 points vertically? Halfway, exactly. So if we cut halfway, actually let's do this graphic style here. This length here is going to be the same as that length there. And well, that means that our height, we're going to have a rectangle whose height is halfway between the first height and the second height. Well, if I've got something that's halfway between the two things, it's going to be the average of f of xi and f of x at I plus 1, f at x sub I plus 1. Well, that makes it really easy, because then our area is going to equal 1/2 those two things together. That's how I get an average. That part there is going to be our average height. And then we're going to multiply it by our delta x, same as last time, which is our width. You can also do it other ways too, if you like. You can take your shape and connect those lines there. You can call it a rectangle plus a triangle, and there's going to be a half, something running around. Gets you the same formula in the end. I kind of like the averaging idea because it's closer to what we're going to see in a second with another technique. And you'll notice how similar it was to the left-hand rule. So this is the trapezoid area. The left-hand rule area was just f of xi times delta x. So there's a pattern, there's a structure, there's repetition in how these things show up when we calculate them.